Okay, everyone, I'll send this by email to you, but these two sheets have got all of the theorems involving circle geometry. So we've grouped them up into theorems involving the centre of a circle. Again, equal arcs subtend equal angles at the centre. Equal chords subtend equal angles at the centre. So there are two theorems involving the centre of the circle. The next one is that the angle at the centre is twice the angle at the circumference, standing on the same arc AB. The next one is that the angle in a semicircle is a right angle. The next one is, I've actually incorporated two parts of Theorem 5 in here, that angles at the circumference subtended by the same arc or chord are equal. And then if AB happens to equal CD, then we've got equal chords subtend equal angles at the circumference, okay? We've got three theorems involving chords, and who wants to go? Go. The line perpendicular to a chord, this one. The line perpendicular to a chord bisects the chord. This one. Chords distant from the centre. So equal chords, so for example if AB equals CD, then equal chords are equidistant from the centre of the circle. Whoopsie. This is the product of intersecting chords. So the rule is that AP times PB equals CP times PD. And that is the product of the intercepts of intersecting chords are equal. Girls, you've got all these theorems written down. You need to look at that sheet, have your little booklet next to you, and look at these diagrams and be able to, because that's what you'll see in a test. You'll see those diagrams with other bits all on top of them, but you'll see that. And then you've got to practice saying the theorem when you see that. Yes. Yep. So there are three theorems involving chords. Then we've got one theorem about finding the centre of the circle, is that if you've got 3 points A, B, C and they're non-collinear, then the intersection of the perpendicular bisectors joining the points is the centre of the circle, okay? So make sure you've got your notes there and try and say the theorems off by heart by just looking at the diagrams, then look at your notes and refine it, okay? Now, I know I said 3 theorems involving cyclic quadrilaterals. There's only 2 theorems but 3 tests, so I've broken it up now. So the 2 theorems are that opposite angles of a cyclic quadrilateral are supplementary. The other theorem is that the exterior angle of a cyclic quadrilateral equals the interior opposite angle. The tests now, notice the circles are dotted. So in an exam, you won't see the circles, okay? But you will just maybe have a quadrilateral ABCD, and if the opposite angles of a quadrilateral are supplementary, then the quadrilateral is cyclic. Okay, in the next test, and I've done the same diagram and made a mistake. So girls, I've got to fix that up. That's meant to have the exterior angle. I've copied the same diagram twice, so I've got to fix that one. But it's meant to be the exterior angle one there, so I'll fix that and send it to you. Test 3 is if a chord, like for example AD, this chord, see how it subtends angle X at the circumference and angle B up, and this angle X here, there. So this chord AD, coming off chord AD, we're subtending this angle X and this angle X. So if an interval, remember the circle won't be there. This is a test to say that that's a cyclic quadrilateral. So if an interval subtends equal angles on the same side of it, then the endpoints of the interval and those other 2 points are cyclic, or the 4 points form a cyclic quadrilateral. Okay, sorry about that test being wrong. Okay, then you've got the 5 theorems involving tangents. What's the first one? Tangent to a circle is perpendicular to the radius through the point of contact. The second one, tangents to a circle from an external point are equal. This one's external contact, but when 2 circles touch, the line through their centres passes through the point of contact. Or it's the 3 points are collinear. When 2 circles touch, the line through their centres and the point of contact are collinear. That'll do. Okay, one sec. the angle between a tangent and a chord, because is equal to the angle in the alternate segment. Okay? And theorem number 17 is that this one squared equals PA times PB. So the square of the tangent equals the product of the intercepts of the secants, or the secant intercepts. Okay? So the square of the tangent equals the product of the intercepts of the secants. So it's PA times PB is P, is that a T? Or whatever it is, PT squared. Okay, so I've just got to fix up that one that's wrong with the test, because I've got the same test twice. And so I'll just fix this up and send it to you, because that's obviously the same test as that one. So a bit of a mistake there in my cut and paste. Okay, girls, this is 2000 HSC question 5. Look, we did start this question yesterday, but it didn't record, so I'll just quickly go through what we've done. The first part of the question was to show that angle PBA, so we had to show that angle PBA is equal to angle PCB. Okay, what we started with, I think, was we said that we've got parallel lines there, so we said for part 1 that angle TPA is equal to angle, what did we get? Angle PCB. Reason was alternate angles. PT is parallel to BC. So we've got that those two angles are equal. I'll call them X. And with the next part of the question, we have to show that PBA is equal to angle PCB. We've also got that this angle here, X, is the angle between the tangent and the chord, and it equals the angle in the alternate segment. So we've also got that angle TPA is equal to angle PBA. Reason, the angle between, I'll just move this up, the angle between the tangent and the chord, so tangent PT and chord AP equals the angle in the alternate segment. Now for part 2 of the question, we have to deduce that PB squared equals PA times PC. Now, when you see something like that, it often arrives